Hello everyone, this is Paul from First Attack. Thank you for watching the video. Here, let's prove theorem 1.1. This theorem just give us basic fundamental properties for the Euclidean space and space. And we do have 8 properties. And these properties are fundamentals. Especially important when we extend the Euclidean space to general vector space. Okay, these will be the 8 axioms. So let's see what's the name of these properties. So we can see that the UVW will be the vectors in space and the C and D scales. And the first is U plus V equals V plus U. That's called a commutative. Okay. The second, associative. So I think everyone, we are familiar with this property, right? And the third, we can say that's 0, right? That's 0, or 0 vector, basic property. A 0 vector also we call identity of addition. So we have 2 type of operation in basic Euclidean. Okay, one is addition, another is scalar multiplication. The first 4 is for addition. So can you see? This is for basic addition. And these 4, the second 4 is basic for scalar multiplication. Okay. Okay. And therefore, 0, usually we call the identity of addition. Identity of addition. D, so U plus negative U equals 0, of course, 0 vector, okay, because negative is the negative vector, okay, we put a negative to each coordinate, okay. So this negative U usually we call negative vector, which means in the Euclidean space, any vector has a negative vector. E is distributor, and right, we can distribute a scalar number to addition of vectors. F is also called distributor. Okay, we distribute right distributor, and distributor vector U onto the sum of scalar addition. G, so you can see CD are 2 vectors. So we do have 2 operations. One is a scalar multiplication vector. Another C times D, the basic multiplication we learned, okay, and the number field, a basic scale, a real field. So look like associated works for both of the operations. So it's consistent or compatible. So G usually we call it compatibility. Okay, so we can say compatibility. The last one times U equals U. Yeah, that one we call the identity of scalar multiplication. Scalar multiplication. And how to prove this? This is fundamental. It should be easy to prove. Okay. The basic idea to prove equation is a look at if the left sides go to the right side if they are equal. So you can move from left to right or from right to left. Use the basic properties we learned about the numbers. Okay. So let me just basically do the proof. I believe everyone you know how to prove. Okay, let's see. Is this true? Look at the A. First let's set up. Okay, because this is the n space, so we can generate setup. Okay, use a vector. I use a color vector. Okay, to describe. Probably a little easy for me. That's U1, U2, to un. See, that's vector. And the v is a general vector in space. So let me use v1, v2 to vn. N coordinate. Yeah, one more w. Okay. Let's say w1, w2 to w. And the c, d are scalar numbers. Now we can do the first. Commutative. Is vector addition commutative? We look at the left. So u plus v. We have a definition, right? Okay, which means this vector. Add all the coordinates together. See, that the first u1 plus v, u2 plus v2 is the second. Goes on. plus vn at the right. Oh, is this equal to right? Yeah, definitely. Well, because see, number addition has a commutative property, right? So we can switch the order of this. Then there's v1 plus u1, and then v2 plus u2 goes on to vn plus un. Yeah, this is commutative for numbers, okay? For number additions, and now by the definition, this will be v vector plus u vector, right? That's v plus u. And then we done the first. Okay. The second associative is the same. Okay. Associated with u plus v, you can associate this first, do this operation first, or you do the operation on the second first. Let's see. So we do u plus v first. After this, we plus w. What do we get? You can think about it, okay? That's easy. U plus v, which is u1 plus v1, right? After this, then plus w1. See, I get the first. The same, I get the second. Goes on the last coordinate. So now is number addition. Do you believe number addition have associated? Okay, so we can associate v and the w together. Therefore, this one goes to u1 plus v1 plus w1. See? So we are very familiar for this, right? Okay. And then u2. Associate v and w. We do this operation first, and that goes on. u1 v1 vn plus wn. We have this, and by the definition, so now the first is a u vector, but we have to do operation, which is v plus w first by definition. See, that's associated. The third is 0. I think 0 is obvious, right? So u plus 0. 0 vector means all zeros, okay? By definition is a u1, u2, plus 0, plus 0, un plus 0. Of course, equals u1, u2, to un, which equals u vector itself. That's true. I look at the d, it's a negative. So what is negative? U plus negative u. Negative u in Euclidean, okay, we have a definition. See, u is a u1, okay, and then negative u1, okay, so negative u1. See, u1 plus negative 1, which is a u1 minus u1 is a 0. Okay, so we will get the first, and then u2, negative u2 goes on to un, negative un. Oh, that's zero vector. Okay, that's true. And the distributor. So let's look at the distributor now. We distribute um, a scalar number. Let me see, it's called a C, right? Yeah, we distribute C to U and V. C times U plus V. Oh, how I can get it? Definitely it's C times the sum of the vector, which is U1, V1, U2, V2, goes on to UN, Vn. Yeah, and then scalar multiplication, we definitely have this C U1 V1 C U2 V2 goes up to C UN Vn. Now do you believe we have a distributor? We learned that from elementary, okay. And we can use a number distributor. Okay, so we have C U1 C V1 C U2 C V2 goes on CUN CVM. That's the one. Now, by the definition of addition and the scalar multiplication, we definitely can break it down into two. One, okay, I skip a little bit. Okay, so C times U1, U2, UN, and also C V1, V2 to Vn. What is that C U plus CV, which is true. We can distribute it, right? And another distributor. F. We distribute two scalar number, let's call it CD to, okay, this distributor, okay. Probably you can say the right distribution. And then what do we get? So by definition, scalar multiplication, right? That's C plus D times U1. C plus D times U2. C plus D times UN. See, they are the same, okay? All numbers, C, D, U1 are numbers, so we can distribute it, okay? So every distributor, we do have this. We have C, U1, D, U1, C, U2, plus D times U2 goes up, C, UN plus C, no, sorry, D, UN. Can you see? And one is addition, another is scalar multiplication. Definitely we can put this C times U1, U2 to UN. Then D times U1, U2, C go to UN. What is? That's C times U plus D times U vector. Can you see? We can distribute a U to CD. So that's true. And G, so compatibility, okay, CD. Let's look at one more. So we have a, let me see, G, right? Okay. Compatibility says C times D, U. CD are scalar numbers. Okay, you can kind of associate C and D together. Is that true? Let's do calculation. What does this mean? By definition, this will be C times D U1, C times D U2 goes on C times D U, and See? When you associate it, so that I can put a CD together, which is a CD parenthesis U1, right? CD parenthesis U2 goes on. To CD UN. Now, by scalar multiplication, that will be C D times U vector. Okay, that's U, the last. I done did it. I done did it. It is as a number 1 times U. Yeah, of course. Number 1 times U is 1 times U1, 1 times U2, goes on, 1 times U. And this definitely equals U, right? Okay, see, that definitely. Okay, so that approved. Thank you.